so we'll start the afternoon session continuing on with magnetic fields and Josep Miquel Girart.
Okay, thank you very much. Here you have the pictures of the three arrays I used to do polarization observation. But first, one thing, of course, here you have FA 101 with Paul Hall. But when I saw that, I didn't think about Paul as a godfather, but Paul as a King Kong, right? So, okay, the other thing is what you see happening here with the full array. That's when we started to do polarization. But my PhD was before that. So maybe Jen she already talked about working with hard-grid with 2 antennas. I was working with, for the PhD, with 3 antennas only. So you have multiple configurations. And not only that, but with Paul, he gave me some data with a source in Orion with a deviation of 0 degrees. So you just can imagine a source with 0 degrees, side off like 80, 90% of the main beam. Okay, and then of course the only way is try to combine with 5 points data, and because it was a mosaic, right? So it was kind of a hard way to then interference. Okay, but of course you always have the two things, right? So now here we'll focus on magnetic fields. So we started with BIMA, with Ramos Rao and Sipin under the supervision of Nick Ratcher. Then of course SMA came, and because there was a lot of need to study the polarization properties of this class, there was installed the polarimeter for SMA, and we took advantage of that. And then of course then ALMA came. Okay. So the main thing to study magnetic fields that I'm talking about start forming regions in the galaxy to understand the role of magnetic fields, right? So which are the tracers to study magnetic fields? Well, before you think about tracers, you have to have a good dinner. So this is from yesterday, okay? And yes, we care about magnetic fields, but first we have to have a good dinner, right? So let's show this. So which are the tracers to study magnetic fields and star formation? So basically you can use molecular lines to do polarization, Lorentz graphics, Simon effect. You can use dust emission to do a line range with magnetic fields, and you can use also extinction. So basically you can do all techniques to try to get polarized emission from here by the magnetic fields. However, I will focus on the dust alignment. Dust particles aligned with magnetic field because this is the more efficient, easy way to do. Okay. But we started with BIMA. I think with BIMA we were pioneers doing millimeter polarization observations with overall. But the difference of overall is that we were successful and we were able to sell many sources and publish even not many papers, but I think they were important. And one of them, I think that's the second paper published with BIMA in polarization, was this prototypical class 0 star, protostar. In that tempo was one of the brightest protostars. Class 0 is very embedded. We detect the Stokes eye, the dust emission is extremely bright, and because of that we selected that, and we could detect the polarization. So here the segment here is the polarization direction of the dust, and if you flip by 90 degrees, you can have some hints of magnetic field kind of out of us, but that's not strong enough. And the other relevant thing we obtained here, because this was simultaneous observations of a 1 millimeter continuum, but we have also the CO in the same setup. We could detect the CO polarized emission. I think that's the second detection of Lorentz graphics of a molecular line emission. Okay. But the good thing is because you have the two things together, we could compare the polarization vectors from dust and CO and see whether the CO is polarized with the direction on the magnetic field or perpendicular, because in the Lorentz graphic you have this ambiguity. The polarization can be perpendicular or parallel, depending on which of the two magnetic levels are more populated. Okay. So what's our relevant publication, but that took a lot of time to get it because we need a lot of sensitivity. After that, we observed many sources, but not many, like a handful of sources observing many hours. Okay, so I think we got some initial relevant studies, and I just want to point out a couple of them. W51, E1 and E2, and this was his PhD was working on one of these sources, where we see polarization for the dust, and this is again, at that time we used to plot the position vectors of the polarization, not of the magnetic field. If you flip that 90 degrees, the magnetic field is perpendicular to the extended filament. Okay. In the atomic watch, what we found is again we could detect CO polarization and dust polarization, and that allows to break the degeneracy in the CO polarization. Okay. So this was I think pioneer work. We couldn't do much more science because we have not many detections, but it was the first ones. So it was starting a new era to study magnetic fields at core scales. And then came up with SMA, and SMA, but the good thing about SMA was in a much better location to study the dust, a much higher frequency, so the dust is much brighter, so it was analytical larger bandwidth in the telescopes, better receivers, so we could really beat the sensitivity and start doing more quantitative science. And in particular, of course, the first object to study was IRS-4A as a prototype, and now with SMA we could resolve the magnetic field, and we saw an hourglass. But this is the expected magnetic field configuration. If you assume that this is the core is magnetized with a relatively uniform magnetic field, and the collapse will drag the magnetic field lines in this kind of hourglass. And in fact, the data was good enough that we could even compare the observations of the magnetic field with the predictions with some relative transfer model of that polarization with the singular isothermal sphere filled by the magnetic field, and see which one of the cases were fitted better the collapsing scenario. So this were, I think, very important results. And of course, with SMA, because of the much better sensitivity, that opens the doors to more quantitative science. And in fact, with that, Qizhou was the leader of a last program to study high-mass astronomic regions with dozens or I think 20 sources. I don't remember the number of that. Right? And with that, we have now quantitative analysis to study which is the overall properties of these massive protostars. And we found is something that was very kind of surprising. So we kind of see a bimodal distribution of the magnetic fields. In some sources, the magnetic field at the core scales, that's what the one that pick up with SMA, was parallel to the large scales magnetic fields. And in some cases, we found that it was perpendicular to the large scale. So it was this kind of bimodal distribution. I think it's interesting. I think it still is not well known why. And the other thing that we found is there is no correlation of magnetic fields and optics. And this is the result comparing the population with the mean magnetic field in the high mass astronomic sample. There is no correlation. And this result was also confirmed with karma observations by Koch, where he has also a significant, statistically significant sample of low mass protostars, and he didn't see any correlation of the alpha axis with the magnetic field. Right? So that gives you some question about whether the magnetic field is really regulating the star formation process at the core scales, right? But now we can ALMA, and we have much more sensitivity, so now we can do a much better work. So that's what we're going to present today. Okay, before that, so ALMA came, right? So you have sensitivity and so on resolution, right? And this is only this like a way to picture that, right? So that means everybody was trying to do magnetic fields at this scale because that's where planet formation is occurring, right? So everybody was very excited, many proposals on that, and then bam, right? What happens? You have large range at the wavelength that ALMA is tracing, that is probably millimeter size range, they have self-scattering very efficient. They self-scatter emission. So what you get from polarization is self-scattering, no aligned waves, right? So this is a new field. I'm not going to go into that. It's very exciting because with polarization you can try to constrain the grain growth at these scales. But yes, for the people trying to understand the relevance of magnetic fields in the distribution, that's really something really worry about. So okay, let's now present the work from my PhD student. So here I say Wang to be submitted next week. In fact, it's this week. So hopefully, probably tomorrow we will submit the paper. It's basically ready. So the box is a work like it's a study we did in more than 50 protostellar objects in Orion. So basically we took the host data and looked for the younger sources, so the one that has a much more dense envelope around the protostars, and try to study the magnetic field at the scales of 400 to up to a few thousand meters. Okay, so in a statistical way, we can see which is the relevance of magnetic fields with the star formation in the same region. And it's a massive region, right? So that's the way we want to go, but this is where more stars are. So 2 minutes, okay, very too much. Okay, so continue, band 7, resolution 407. So let me just go here to the results. So what we found, we could derive the properties of the polarization in more than about, I think, 60 sources, which is a lot, 60 protostars, not sources. So with that, because we have a lot of large sample, and this is a rough approximation, but so there is no clear idealized size of like areas for it. But many of the sources you can classify them in this kind of sources. Like a standard hourglass, that's idealized storage for it. We found 8. Rotated hourglass, now I will show what that means. So the hourglass direction is perpendicular to the outflow, 13 of them. Then a spiral pattern, a clear spiral pattern in 8 of them. And then we have not a complex data or nothing of data in 10 of them, and then 16 sources show only self-scattering. Okay, so now we can do a classification for the first time. So because I don't have much time, let's move. So this is an example, clear example of you have the outflow here. You see this highly polynomial outflow. This is the magnetic field. You see kind of the pinching of the hourglass. Okay, as I said before, this is not as clear as INAF-Osservatorio, but this is a train of an hourglass. And like that, we find like a 7. And in this case, even the main magnetic field direction is along the outflow in this case. Now the rotated hourglass. What I mean with rotated? So if this is the outflow direction, okay, in this case, you see here the magnetic fields, and you see, well, we call it rotated hourglass because the rotation is here, and the curvature of the magnetic field is in this direction, so it's like that. We found many of them. And now going back to the literature, in fact, B55 by is this kind. And there is also 11, 40, 48, I said 2, that are scales than hourglass. When you go to these scales, you see the same. Okay? So it wasn't the first time, but I think we were just thinking in just the standard hourglass, and we have many of them, like 30. And the other time, which has already been published in high mass astronomy regions, the spiral pattern. This is a binary, and you can see the magnetic field just going like a spiral pattern. And we have several of them. Okay? So now for the first time in a statistical way, we can derive the magnetic field. The other thing we did is to try to use charcoal statistical compare outflows with magnetic fields. Okay? We did that in the same way that he did, using the same constraints, and that's what we find. So, and this is the taking into account that the magnetic field and the outflow can be in any direction with respect to the in a 3D, right? So you have to take into account the geometrical effects from a statistical point of view. That's what we find. But so this is a perfect alignment, a perpendicular alignment with the outflow. But remember, we have 16 sources. This is why we are including blindly the self-scattering. And here I show you several sources where we see this is the grayscale here, the color scale here is the polarized emission, and here the vectors of the polarization angle, and this is always the polarization vectors. Yeah, this is the old one, this is the magnetic field. So you can rotate the polarization vectors along the outflows. That means it's perpendicular, it's along the neighbor axis of this, and this is the pattern typical of scattering. In addition, we try to fit which is the size of this polarized emission, we get basically unresolved or in agreement with the D scales. So we are really short, and polarization fraction is also low, less than 1%. So we are sure this is self-scattering. So for the self-scattering sources, there is one source that is an outlier, but if we do the statistics, the mean difference of the disk and the polarization angle from ALMA, the disk is from the Tobin survey, the mean difference is 85 degrees. So the major axis is 85 degrees with respect to the polarization angle. If you compare the difference of the outflow and the polarization, the mean difference, excluding this is 7. So basically, these position angles are very well aligned with the magnetic field. With the outflow and perpendicular to the major axis of the disk. So this is the standard case of self-scattering. So there is no doubt that this is self-scattering. So after we subtract the self-scattering and we do mean values of the magnetic field, avoiding the center because we may have for the rest of the sources self-scattering, so we start doing the mean, the average, the magnetic field average above a radius more than 400. Then we found basically when we compare the outflow and the mean B field direction, we see some kind of randomness distribution as periodically observed, but we see a trend that some sources are perpendicular to the outflow. And with that, because now this is the cumulative distribution function of the difference of angles, excluding the self-scattering. And this is the conclusion. So now I think now with ALMA we can do really surveys in a statistically meaningful way, and at least for low mass we have seen that the magnetic field comes basically from three types of morphology, which is probably the initial condition. The spiral probably is because not only gravity but also angular momentum is dominated. The inverted hourglass, I guess, either is toroidal, or is because you have extreme hourglass. And if it's extreme, basically close to the protostar, most of the three lines will be along the middle. And that's all. Thank you.
It's a very nice talk. I would like to ask, what do you think was the origin of this angle difference between the mean polarization and the outflow? And do you think that's robust? The reason I ask, because tomorrow I'm going to present a polarization measurement toward the disk, which will exactly found a deviation of 7 degree with some expected B field direction.
Okay, so you mean for the disk at the disk position?
Yes.
Yeah, okay, so what I'm presenting here is only on the top panels, only sources where the polarization is coming from unresolved polarization. So it's coming from the disk scales. When we include at the center all the sources, because you have self-scattering, you also have a line range with the magnetic field. When you do the same statistics at the center, you have the contribution from a line range, then this random. So because you have the spiral pattern, the pattern will, the average value will point in a different directions. Okay.
All right, one more.
So these are only for the one that we know that is only self-scattering.
I just have one quick question here.
Yeah.
Okay, so when you observe the different patterns, do you have any correlation with the strength of magnetic field?
I mean, this is the first analysis, so we haven't still used the magnetic field strength. Okay, so that will be the next step to do in the second phase for the PhDs. But of course, we can use this localized magnetic field using the technique by Hong Kong or another technique like the Patrick Wang to try to estimate locally the magnetic field. That will be the next step. Yeah.
Okay, let's present questions. The next talk on the schedule, general stay is canceled, and we're going to move on to Jia-Wei.
Hello everyone, my name is Jia-Wei from ASIAA, and today I will talk about new result from the BISTRO survey. So BISTRO survey is one of the CSIC surveys, so we are trying to plot the magnetic field in different types of scattering region. And at first we are targeting the molecular clouds in Global survey, they are mostly low mass regions, but later on we are trying to expand our targets to like for massive region, we also include the distant clouds, Hopkian system, and IEECs. So now we have a variety of objects in our survey. And in this talk, I will mainly focus on this source, NGC274. This is the massive region, this is the massive star-forming region, and it is important because this is showing the typical Hopkian structure. So as you can see, this is the partial image. You can see there are two big two massive clouds at the center, and there are several extending filaments on Pascal scale that is connecting to its central hub. So it's forming a very typical hub filament system, and this system holds at least two block clusters at the center. So we would like to know how the block cluster is forming in these regions. So here it just shows the projection from JSNT observations, and here the green segments shows in the large scale magnetic field transcribe count, and the yellow segments are the projection segments from the JSNT pole 2. And as you can see in this region, it shows that the magnetic field here is quite organized. So also if there are mixed some region here, but in most of the region, the magnetic field are quite organized or even uniform. Also, if you compare the local magnetic field to the large scale magnetic field, you can find that they are actually not consistent. So the local magnetic field, they should be modified by some mechanism in the local region, so it's decoupled from large scale magnetic field. And in the previous talk, Josep Miquel has introduced the history from BIMA to ALMA, and now we are in the era of high resolution, so we can actually have hundreds of projection detections over the whole map. So in this era, we can do one more step than the early studies, that we not only describe the overall magnetic field flux, and now because we have very good data, so we can really look into what happens in the local region. So in this work, our focus is to try to figure out how the magnetic field and gravity affects the local density structure. We can do this analysis pixel by pixel and to really know what's the physics in the local region. So in order to do that, we need to first extract the density structures. And as you can see, this continuum map is log scale. It is used to show all reliable detections, but actually we cannot really distinguish the density structure very well. So here we show the image in different intensity scale. So in high intensity regions, we can see that there are some dense cones. This is the southern part. You can see there are some dense cones that is lying up along the filamentary structure. While in this case, you can see there are multiple dense cones. They are randomly scattered in these regions. But if we move on to the low intensity region, we could start to see there are actually magnetic structures that are connecting these cones. So here in the southern part, you see there's massive filaments that is connecting all these massive clumps, and there are some low intensity filaments that is extending from the clumps. And in the northern part is more complicated. It shows a quite complex filamentary network, and this filamentary network seems to converge into all these scattered clumps. So we can first give a quick overview by statistics over the orientation of the filament pixel by pixel. And here just shows the comparison between this is the filament orientation, this is the magnetic field orientation, and this simple histogram shows that for filaments we actually have bimodal distribution. Most filaments are either picked around 40 degrees, that is this direction, and or 150, that is the other direction. And the magnetic field area actually has the prevailing orientation that is also around 50 degrees. So it's already implies that the filaments in the magnetic field, they are actually correlated. And we want to know further how the gravity is involved in this process. So here we try to give a parameter that can use to estimate the gravitational field. So now we get the intensity map. So here we try to calculate what we call local gravity. That is this vector sum. So for example, if we have a pixel here, we calculate the gravitational force from all pixels over this map toward one pixel, and we calculate the sum of the total gravity. So here this vector means that for all the summation of the gravitational force onto the pixel is pointing toward this direction. So from this map we can roughly know that in the southern part, the gravitational field is mostly pointing toward this massive dense region, and they will eventually converge to this massive region where we can find the most massive protostar in this cloud. On the other hand, in the northern part, we can see the gravitational field they are actually converged to multiple conversion points. That's what we label the C2 to C5 here. So the next step is we have filament, we have magnetic field, we have gravity, we have these edge parameters. So we can first see what's the overall distribution. And as I have already talked about the one for filament and magnetic field, we can find that for gravity it is also showing the major peak that is around 50 degrees. So from this histogram we can already know that these three parameters they are actually quite correlated with each other. And to do further, we can really see what's the relative orientation between the magnetic field and gravity. Then we calculate the relative orientation pixel by pixel, so we can get this relative orientation map. Here, the blue color means that the relative orientation is about 0, so they are parallel, and the red part is perpendicular, means they are not perpendicular. So from this map, you can see that their relative orientation, this relative orientation is unrandom. They have shown some pattern. And one of the clear patterns that you see, they are certain filaments. They are actually really consistent with the red color. And some of the filaments, they are actually more consistent with the blue colors. So to figure out what's the origin of this to determine these features of related filaments, we also compare to what we usually do in the early studies. We want to know what's the alignment between the filament and the magnetic field. So we do the same thing that we calculate the relative orientation between filament and magnetic field. We plot it on map. So as it shows in early papers, we can show that some of the filaments they are red, means the filament is perpendicular to magnetic field, while some of the filaments are more blue, means they are parallel. And if you check the cross correlation, the gravity was magnetic field, the magnetic field was the filament. You can see that the sum of these red filaments here are actually quite consistent with the red filament here. So we can find that there are some two different kind of filament that can be identified from this cross correlation. So to do some statistical work, we have really plot the relative orientation from each clump, from the filament magnetic field and gravity versus magnetic field. And here each dot is 1 pixel, and the color here is the density of the pixel. So we can clearly see there are two clusters, right here and here, and we just label them as type 1 and type 2. So type 1 here means that the gravity is more perpendicular to magnetic field, while the filament is also perpendicular to magnetic field. On the other hand, for the type 2 filament, the filament is parallel to magnetic field and gravity. So to really know what's the physics inside these two types of filament, we have selected two regions as an example. So this is one example. This is a type 1 filament. You can see that here the green line is the filament, and the yellow circles are the magnetic field. And for filament and magnetic field, they are roughly take the same orientation. But what different is the gravity, they are actually starting from conversion to a filament, but when you go into a filament, it becomes parallel to gravity. And this is why we can see the transition from blue to red in the magneto-gravitational configuration. And for type 2, they are much more simpler. You can find that almost all of region, the filament, the magnetic field, and the field are all aligned together. So how to integrate this configuration? We can try to explain this using the filament accretion mode. Because nowadays there are more and more evidence to show that the filament in the hot analysis is actually accretion flows. So for accretion flow, we can think about the accretion flow can be separated into two modes. The first one is longitudinal accretion that will basically transfer to the hub, to transfer mass from the filament to the hub, driven by low gravity. So it's actually a mass output for the filament. But for radial accretion, which means that the mass can be radially accreted onto a filament from the real mass, and this is actually the mass input of the filament. So we have output and input, then we can directly imagine that when the input is output, then the filament can start to grow mass, and if the filament is massive enough, it can start to filament and form stars. And this is actually how we see the type 1 filament, that we see efficient accretion radially. We see the radial gravity is quite efficient. Also, it will eventually be cancelled out and later be dominated by longitudinal accretion. But in type 2, we don't really see the radial gravitational component, and it's really dominated by the longitudinal component, which means in this kind of region, the mass output is actually greater than mass input. So this kind of filament, they are mostly low mass, and they could disperse if they have just too much mass to the center. So this is our main conclusion here. Thanks.
Okay, questions?
So I have a question. So about the filament, do you have kinematical observations where you can prove what these filaments are doing, if they're creating streamers of filaments or not?
We have the kinetic data, but we can't put it in this paper because we actually find that in this curve, in most of the region, there are multiple components, so it's actually really difficult to really extract the velocity, the knowledge of the gas velocity. So yes, that's our future plan, but it's not done yet.
Any other questions? Oh, there's one.
So in this figure, you divide into type 1 and type 2. Then is there any difference in color density in between type 1 and type 2?
Yes, actually, we have separated these points with high density. We can see that these type 2, they tend to happen in the low density region. Type 2 type 2 tend to be low high density, but type 1 is in the higher density. But their boundary is actually not really clear. They are overlapped quite a lot, so we cannot really say a boundary in color density.
Okay, let's thank Hsi-Wei Yen. And our next speaker is Patrick Koch, our LOC co-chair.
Okay, thank you. So I will be talking about magnetic fields as well, but with a somewhat different focus. So that is the local description of magnetic fields. And I will show you exactly, I will illustrate that a bit more on one of our favorite sources, which is W51, which we have been observing over the last 15 years with Paul, starting with Tantan's PhD thesis. So what you're looking at here is the streamlined visualizations of the actual observed magnetic field. So, and we're going from the coarsest resolution here to the latest ALMA resolution towards the right. And you see this is about 3 arcsecond. This is 0.1 arcsecond. So there's an improvement in resolution by a factor of about 1,000 in area. So this is a high mass system. So this is the elongated envelope. So in the north is E2, in the south is E8, and then we are gradually increasing the resolution. So this is actually SMA. This is also the highest resolution of the SMA, 0.7 arcsecond, where we see the actual pores, how they collapse. And then with ALMA, we are going further and further to resolve these structures more. And so what you should take away from these maps, I hope you can see this, there is really a wealth of structures in these magnetic fields. So, and that's the motivation for this local description. So we heard from Qizhou before about the Davis-Johannes Fermi method, which is a statistical method, and we try to do something different because of this very detailed structures that we are seeing. So this is the motivation. So these detailed morphologies, they carry the imprints of how these systems are formed. So that means what we are actually seeing is how forces that shape these systems, how they interact in the planar sky. So that's the whole motivation to have something that is locally really measuring what's going on, instead of just having this Davis-Johannes Fermi method, which typically just gives you one single estimate of magnetic field strength. So this has been the focus of this work for about the past 10 years. There will be 2 main results that I like to show. So first one is a multi-scale collapse within collapse picture that I will illustrate with a series of observations. And then the highest resolution observations, they are showing what we think are B-field stabilized streamers. And all the analysis that we will do is the localized analysis. So this is W51. Some of you know this. So Qizhou has been working on this also with Paul. This is a high mass system. So E2 up here is about twice as massive as E8. So the contours that you see here are the early BIMA results from shipping, which basically show a magnetic field that is perpendicular to the lower axis of the envelope. And this higher resolution, this red one, is the result from Wang's PhD thesis. It shows the E2 pore and E8 in the south. So the one thing I want to emphasize here is you should carefully look at the BIMA data. So you see that here, where actually E2 shows up, there is no white segment. So this is a polarization hole. So if you are sitting on a TAC or any other review committee, if somebody says they want to observe polarization where there is no polarization, remember that this is what you will get. So no polarization and coarser resolution doesn't mean that there's nothing at higher resolution. So this is because the higher resolution polarization cancels out in a larger beam. So this is really important. So this first main result, so again, so these are the actual observations. So whenever you see segments, these are the magnetic field orientation. So as going back to Josep Miquel's presentation, so this is rotated by 90 degrees from the originally detected polarization orientations. So now we are looking at the envelope scale. So this is the BIMA, this is the SMA subcompact observation, which shows a bit more on what is happening between this and this pole. So we're looking at this region, and now we're looking at this scale and at the next smaller scale where we see the locally collapsing cores. So now let's look at this, how this works with the local description that I was mentioning before. So this is our framework. So in red, This is the detected magnetic field orientation. So the dashed line orthogonal to it is the direction of the magnetic field tension. So the black vector is the direction of local gravity. So you imagine you're sitting here, and so this is the force that you would feel taking into account the mass distribution around you. So this is where direction, this is the direction, this is where towards the direction that gravity would pull you. Okay, so you have competing forces, the magnetic field tension, and there's a local gravitational pull, and then there's some angles that you can calculate, and importantly for here, for this work here is omega, and specifically omega and sinus omega, because sinus omega measures the fraction of the local gravitational pull that can work against the restoring magnetic field tension force. So if gravity is just product to the magnetic field, no? It just pulls along the field. While if it is perpendicular, then you have a very different force constellation. And so that is the key for we are doing this for this work. So the two scales, envelope scale, so E2, E8, so this is the local collapsing core scale with the high resolution, so you see the core E2 breaks up into several smaller cores. Now, E2 is about twice as massive as E8. So if you look at the gravitational vector field, so the black arrows here, you see that this is like perfectly symmetric, everything pointing to the center. If you look at E8 in the south, this is also converging to the center, but then here in this transition zone, the vectors are actually turning around. And this is what you would expect because gravity is just stronger up here. So this is pulling towards this side. Now you look at the next smaller scale, you actually see the same thing. So between E2 west, E2 east, E8 south, you see the field again is converging from the south, but then here it's opening up and going towards E8 north again because E8 north is more massive than this one. So you see these recurrent structures on different scales. And this is something that people doing numerical simulation have noticed, and they've called this a multi-scale collapse, living collapse. So what we are adding is the magnetic field. So this is again E2, so you mostly see something that is like an hourglass. In E8, you see something like an hourglass in the southern part. But not here. Now here the field is straightened and it's opening up and again like being pulled to the upper north and more massive part. And if you look again at the smaller scale, this local collapse, you actually see the same. There's a bit of an hourglass here, the field is opening up and being straightened to the more massive northern system. So the magnetic field structure also varies or changes in a way that is very systematic, and it seems to be again a recurring structure of these different scales. So now we're looking at omega. So omega, the angle omega is the angle between the magnetic field and gravity. So here again is the gravitational vector field, here is the magnetic field, and so this is the sinus omega map. So the first thing to notice is sinus omega is not random. Now it has very clear structures. So in blue you see the values close to zero. So that means magnetic field and gravity are mostly aligned. And the yellowish orange colors are where they are mostly perpendicular. So this really measures the competition between the magnetic field and gravity in the plane of sky. So sinus omega captures this local competition. And so there are areas where material can more easily go flow from one area to the other, and there's clearly areas where there's much more work to be done to actually overcome gravity. Overcome the magnetic field. So let me go to the latest ALMA result. So this one here, so again this is the magnetic field in red, and what you see is these streamer-like structures now. So for a comparison, so this is ALMA with 0.26 arc second resolution, so we already see this overall global core resolved into these three structures here in E2. And then once we go to the 0.1 arcsecond resolution, there's two main results. So first is that the source does not seem to fragment more. The other one is the more roundish diffuser structure is resolved out, and we start to see these fingers or streamers. And of course now we see the magnetic field that is really mostly aligned with these protrusions and fingers. And additionally, in E2, we think that actually what we start to see is a disk-like structure. And there's very interesting, there's SIO outflows, and they are just originating from locations where the disk is sitting. So now let's look at this local description for this constellation. So what you have to take away from here is the fact that we have the magnetic field aligned with the streamers is very different from just a core if the magnetic field is aligned like this. No? This core is azimuthally symmetric, so it doesn't matter how the magnetic field is going through the core. But once you have a constellation like this, it matters, and that is because local gravity is mostly pulling along this direction, right? Because here is the center, more massive thing, and so it matters how local gravity is aligned or not aligned with the magnetic field. And in order to have such a structure collapse or destabilize, what matters is the force or the fraction of gravity that is able to overcome the magnetic field tension, so then it's perpendicular to the line. And so this can be translated into a formula that is here, so that gives you a limit of the magnetic field strength, which depends on this local gravitational force that we can calculate, and the angle omega, so the angular energy magnetic field, and the local gravitational vector field. So if we do this for E2 and E8, so here's the result. So these are the limits for the magnetic field strength that we get, and we see that these numbers are of the order of 100 microgauss. So now, what does that mean? So, going back to the literature, so these are Siemens measurements or measurements from Tantan's work, so we know that the field strength here is a few gauss, or up to 10 milligauss. Not a few milligauss, up to 10 milligauss. And so we find that 100 microgauss are actually enough to stabilize these streamers. So 100 microgauss is enough so that gravity cannot make these filaments or these streamers collapse. And so that means that this network that we start to see, that we start to resolve, is probably stable. In other words, this is probably a network of accretion streamers. So this is how the material gets to the center. So it's not a nice spherical collapse, but there is like selective channels, and these channels are stabilized by the magnetic field, which is prevailingly parallel to these streamers. Okay, so this is my conclusion. So there's distinct scales, regimes that we have resolved, going from 3 arcsecond to 1.1 arcsecond. One of the things I'd like you to take away is that the magnetic field is playing, or it can play very different roles depending on scales, but also depending on the actual location in a source. No? So this is what you would not get from Davis-Chandrasekhar Fermi, where you just get one number. No? So this is where the local description really adds a lot to the physics. So for this analysis specifically for B-equivalent gravity, design omega is very important. So yes, that's the main result. So also another picture, and I think it's interesting that we see that the streamers, they seem to be stabilized with the magnetic field. Thank you.
Lots of questions. Start with language. Yeah, very interesting. Well, actually, I know what you're working for, this time. I was just wondering, so when you look at the velocity field, like, Magneto-Wang map, Well, basically you can tell which field is deep stronger, which area is gravity is stronger, right, based on your analysis. But when you look at the kinematics, can you see the clear difference between two regions? And each area, you still see the coherent kind of velocity structures?
So for this resolution, we do not have that velocity information yet. And for the larger scale, so here we haven't looked at it. So I mean, clearly there is what people have been focusing on is the E2 here, E8 here, which is, for example, to see the collapse in false signatures in the spectra. But I think a key piece of physics is actually in between here. Right. Because there you see how the material is distributed, and here you see this competition. So this is the place, because once you are in this collapsing phase or close to the densest parts, it's mostly gravity driven now.
Right. But that is what I'm asking. When we are looking at the lower sample region, collapsing core, of course, has a more coherent well structure. Right? But when we look at zoom out, then we don't see the coherent structure and rotation of everything. So, kinematics-wise, may not be so simple anyway. And I was wondering, turbulence kind of things might be very important.
Exactly. So I think for the larger scale, diffuser stuff is difficult to observe, and extracting the coherent motion while there's also turbulence might be a challenge.
So do you have any molecular data to study streamers with big structure?
Not at this resolution.
No. Any plan or proposal? Yes, indeed. Of course.
So I'm wondering, from your current study for different molecular scales, have you have a hint which would set the scale that determines this self-similar structure?
No. So my quick answer would be that there's a repeating structure, and also this so on this envelope scale, there's something further outside that defines this, or there's the initial condition further outside that defines this. And once actually this one develops, this one is like decoupled from this one. So this one again sets the initial condition for what is going on a small scale. So I think maybe the question would be whether these initial conditions are similar. But I don't know that now. Yeah.
Okay, let's thank Dr. Yen. And our next speaker is Qizhou, our SOC coach.
I can talk as long as you want, right? All right, so what I want to talk about today is the from W51 to T10.6. So you already heard a bit of W51. This is a conference actually celebrating Paul's achievement. And in fact, Paul's work is really spread out from known galaxies to small galaxies. But there are few objects actually has been his favorite for a long time. And Orion is one of them. W51 T10.6 Galactic Center. Right? So So this is really a story of pursuit of higher angular resolution to tackle new problems or new questions. All right, okay. So, first of all, this is what Paul looked like at the time in the 1980s. All right, so in the two papers, so one is 1983. All right, he did this work with BOA and ammonia 3,3 in W51. So this is exactly 40 years ago back. So what he reported in this paper is that he detected warm ammonia, the JK level 3,3 line inversion lines that excited with over 100 Kelvin of excitation level. So which is and it's surrounding this object that has a bunch of major emissions. Based on the line list, and he said that this is probably due to the sort of wind-driven outflows. It's a very large line list in this very warm or hot ammonia that's surrounding this cluster of measures. And then later in this paper in 1986, he looked at the G10.6, again in ammonia, a long line, and he reported this spin-up collapse in those regions. So over all this time, so there's a string of students actually working with him, and anybody can guess? So I don't know this young handsome guy in the middle, but so here are the names. So it's Erikito, Lisa Norton-Young, again I don't know this guy. This is Peter Solness, actually, after Balbo and Compound. Of course, you heard a little bit of her work. And the latest, that's the Charles Lowe, who just graduated from Harvard. So there were 4 Harvard PhD theses actually were subject studies of W51 and G10.6. And also the 2 PhD theses actually from National Tsinghua University. All right, so this was the work that I did with Paul in the 1990s with the BOA. And in fact, at that time, this is a centimeter continuum emission. It was actually have to get the line free channels from those not very broad bandwidth in there. And as you can see, that this is the continuum emission, mostly from this IS1 and then RS2 is coming from the free emission from ionized gas. And my contribution is actually, one of the contributions is identified as the E8, because before that, people think that this is from mostly the E1, that's where the dense molecular gas. And you can see that, you see this ammonia gas, and in a long one that's surrounding those H2 regions. So we look at the line asymmetry in a bunch of the spectrum, of course, including line emission from ammonia with BOA. You can see that in the E2, you see this inverse designing profile towards the very dry H2 region. And also, using an Obiama, we look at a bunch of lines at 2 millimeter band. And this is actually my first collaboration with Naoyoshi, and took the first trip to Obiama, and it was a lot of fun. But anyway, so you see this line asymmetry that consistent with sort of gases infalling towards the center of the gravity. And really combination of excitation and inward motion and varying optical depths to give you this varying asymmetry in different lines. All right, I will not go through those in details. I'll just sort of demonstrate that sort of what technology can actually get you. You can see that when you look at high-end resolution, or using the, this is some of the work done with both JBOA and ALMA. So with upgrade, you see a lot more lines actually, simultaneously with BOA. So we're able to actually see a lot of high JK level ammonia in this region. You can see that you still see there's very warm gas around E2. And as Patrick mentioned in this talk, when you look at high resolution, in fact, this E2 is really broken into a lot of fragments, including, this is called a shell-like H2 region, and then you have this more embedded objects that mostly consists of gas in the dust emission. So what info that we see initially, we thought it was a single object, actually is the class info towards a group of objects in here. And again, you see what technology brings you. This is the using the expanded wideband VOA, and this is the beautiful map done by BISTRO. You can see you detect a lot more compact H2 or ultra compact H2 regions around this extended emission in this region. All right, so let's look at the G10.6. This is what Eric looked like when he was a graduate student. So Eric, actually following Paul's work, Eric looked at this in higher JK level ammonia. As you can see, this is the position velocity cut along this axis. Again, this is 1.3 centimeter continued emission here. And what he did with Paul was they recognized this kind of C-shape, tilted C-shape of the gas in emission, and that is the signature of both of the rotation, right, surrounding this absorption that was redshifted against H3. So that's the inward motion with the rotation here, and you can see also when you look at this at the high-end resolution with in ammonia in absorption, and you can see that actually you're also resolving that absorption signal that have the backside of the C shape, and that tells you that you have this sort of radial inward motion of molecular gas towards the H2. All right, so this is what technology actually can do. This is Peter. It's working around 2000. As you can see that you see this is a Connie low resolution continuum map. And when you look at the 0.1 second resolution with VOA A array, you see this really a lot of ionized arc around this region here. So this is the bubble came line. That's when the SMA actually came online, and you look at this region both with in the larger scale using the RN30 meter, and this is what's shown this panel A. In fact, you do see the central H3, the G10.6 is connected with this filamentary structure, probably is transporting the gas for the center. And then at the center region, of course, this is the part of the work that Peter did. In the contour is again this is the VOA continuing emission here that you see the ammonia actually in absorption. When you look at optical depths, it's very patchy in here. So with the SMA, you actually detect a lot of dense molecular gas surrounding H2 region in different tracers, including, for example, CS here, and then in methanol, you see this is a cavity that actually is evacuated by ionized gas in here. It's very, if you ignore the spatial scale, it's very similar to what you see in low mass stars. That you see the flattened envelope, and then you have the outflow axis, except that the mass scale is a lot bigger. And we're talking about a few hundred solar masses forming in this H2 region. All right. Okay, so one of the questions is that you see this gas inflowing towards the compact H2 region here. So the question is whether this ionized gas actually, the gas will continue to accrete in the central cluster in the ionized gas form. The question here is that when you form more massive objects, say 25, 30 solar masses, there's sufficient radiation ionization to ionize the surrounding of the molecular gas. So the question is, how do you form stars more massive than 20 or 30 solar masses? And you have to accrete in ionized gas. And this is really lack of observational evidence so this was the motivation of a work using ALMA here. So as long as we look at the H30 alpha lines, here again, this is the molecular envelope that reported in Bauhaus work. And this is a zoom in the H30 alpha. This is an indicator emission. And if you recall the VLA map in 1.3 centimeter from Peter Solon's, this is very similar. You see those ionized arc here. This line, you have a recombination line emission associated, coincide very well with the ionized emission. So when you look at the central region here, and this is the position velocity cut in H30 alpha, you can see that this is a very nice tapering-like motion here. And except that this is the calculated about 200 solar masses to binding mass in here. And this is a work actually involved a few people, and this is Roberto Galvin Madrid, which is also a former student at Koch supervisors, Paul and I. And also this is actually the student working with Roberto, and this is Charles Walnut, who's a PhD student working with me at Harvard, who graduated recently. So this is 3 generations of academic generations of people involved in this. So we did, we tried to model those emissions, use the non-LT rate transfer, and also couple with the Markov chain Monte Carlo search for minimization of parameters. And in fact, we were able to constrain the binding masses in the about 200 solar masses to produce this kind of signal here. And also that's consistent of several old stars of 20 to 60 solar mass. All right, so this is all the story that sort of involvement. I was very fortunate to be mentored with Paul, but later as a colleague that working with him and continue to supervise students. So what else I've done? The remaining time, just briefly on some of the objects. So I talked to you, this is sort of a cartoon to show the evolution of formation in time sequence for massive stars and protocluster. So this is the H3 region, ultra-compact H3 region that goes W3RG10.6 for forming categories. And I've been also spent a lot of time, more the past decade also, trying to understand the formation of protoclusters at very early stages. So I want to just flash out a few things done. We're looking at the gas structures and thermodynamics in those infrared dark clouds. So those are massive clouds are supposed to be region that forming young massive stars and protoclusters. I will not go through those in details. The other things that we spent a lot of time was actually looking at magnetic fields, and for some of that has been discussed in Josep Miquel's talk and also in Anna's presentation in the morning. I would just sort of flash out some of the work that we've done recently. This is the work that we did with SMA in Lodge. Was the one of the legacy survey there, and this is the follow-up with ALMA in NDC 6334. And so again, I will not go through details of those. I just want to show Paul that I've not been sleeping all the time outside of working on that G10.6. So this was a photo that we might have seen in one of the team meetings actually we had at the ASIAA. All right, so I just want to say that thank you for all what you've done for me, and happy retirement. In quote.
Questions?
So that's a very good question. Have you ever been able to properly map the molecular outflow in G10.6?
The outflow, we do see outflows actually, but it's not centered around H3. There's another small group of objects are forming in the field that we detect those outflows from the SMA that Maobo reported in his publication, and we also send that with ALMA. But in the central region that you see the ionized gas, no, there is no clear signal of a CO outflow, say in CO.
Yes, I got asked always the same questions. So when you look at the rotation curve, do you try to fit as rotation with conserving angular momentum?
So we had, I did not go into detail, but we had several models that, including auric flow. This is the paper that auric that you have the gas infalling in trajectories, and then added with the disk. We have a few dynamic models, and then feed it into a rate transfer, a nominal-T rate transfer.
More questions?
Okay, now let's thank Qizhou again. And we'll move on to the next speaker, Hsi-Wei Yen.
Okay, so I want to start with a few words about how I met Paul. So, I was an undergraduate student here in this university. I was in physics department, and at that time I know nothing about astronomy. I had no future plan. Of course, I did not know Paul. So at that time, he started a journal club, particularly for undergraduate students. So I joined that journal club. So we start to meet regularly. Usually we have journal club every weekend. We have journal club on like Saturday or Sunday morning. And as you know, Paul has been always busy, but still he spent a lot of time to look after us. And a group of undergraduate students, even though none of us really work on a project with him. So I really appreciate that, and thank you for being my mentor for so many years. And I remember the first paper we read is a review paper on star formation by friends through Fred Adams, Susanna Lizano, 1987. And that's how I started my career. As you can see, I'm still studying star formation. So careful with the first paper you assign to your students, but they impact your career a lot. Okay, so today I'd like to introduce my recent work again about magnetic field strength, and by studying the interaction between the gas dynamics and magnetic field. Okay, so we all know the spectrum region magnetic ties is introduced in the previous talk, like the strength, structures of magnetic field, and how well they couple the matter affects star formation process a lot. So here I show two simple examples. The first one, these are simulation. The first one is with a weak magnetic field and allow magnetic field to decouple from the matter, and then the disk is easy to form around protostars. And the second example is with a strong magnetic field and the magnetic field will couple with the matter, and the B field will disrupt the disk formation. So understanding the magnetic field strength around the open disk is important to understand the disk formation and evolution. So there's a few ways to estimate magnetic field strength positionally. As introduced in the previous talk, like the only direct method BIMA effect is dot formation is very challenging to detect. And the other method is DCF method introduced by Josep, and actually it's a quote from his paper. So by studying the fluctuation of the field structures, we can estimate the field strength. And this method being tested using numerical simulation, which can provide a reasonable estimate on a scale larger than 0.1 percent. And the other method introduced by Patrick is using a polarization angle and the intensity gradient. And is assuming like intensity can kind of represent the interaction between the result interaction between the gravity and the magnetic tension. And the other method is actually using velocity information. For example, if we detect inflow velocity slower than the free fall, we can attribute that to a magnetic tension force. So in our study, we combine the advantage of these two methods, try to estimate the magnetic field strength in the inflowing full-scale envelope. The idea is this. It's derived from a momentum equation of the MHD. In simplified one, this can assume the inflow motion is dominant motion, so there's no turbulence here, and we assume the gravity and visual tension dominate over like thermal pressure, magnetic pressure, and so on. So it can be simplified to this equation. So in other words, we're looking at the balance between the gravity and magnetic field tension and the resultant inflow velocity. So we can measure inflow velocity from vertical line, like this method. We can measure mass distribution from continuum, like you can see gradient here. And we can measure the field curvature based on the polarization map. So we select this source. As a famous H-on protostars is the JCMP empty micron map to show dense core around these protostars. Inside dense core is spectacular bipolar geometric outflow. At the center is a 20 AU disk, and this rotation has been resolved, so we know the scale mass is around 0.1 solar mass. So we took the ALMA archival continuum data at 0.8 and 1.3 millimeter, these two images. So we use the sparse code, the radiated transfer code by Smithsonian. We use this code, control a model, we calculate radiation transfer, generate the model image, and sample it with the exactly same the UV coverage of our data, and get visibility to efficiency speaking in the UV domain, and to get this model image. And these two compare intensity profile at two different wavelengths. The black with these gray shaded areas observation, and red is from our model. So from this analysis, you can get density and temperature profile of our system. And the scale here is about like several hundred AU. And once we get density and temperature, we add velocity and do the same thing to fit the ALMA Hsi-Wei data. So here show moment map of a Hsi-Wei, and we compare the PD diagram, the precision, velocity, the black and gray are from observations, red are from our model. And these two panels compare the velocity, and line width is a function of radius between observations shown by this data point and our model shown by these red lines. So our model can produce a key feature, for example, absorption here, a versus velocity, also this asymmetry intensity. So from this, you can get velocity profile. So now we have scale mass from the disk rotation, we have density profile from continuum, velocity profile from Hsi-Wei. So we again get polarization data provided by Qizhou. So we just show the polarization result rotated by 90 degrees. So here I show B field morphology. And I rotate this image, so the vertical axis is a rotational axis or outflow axis. This gray area shows the region occupied by the outflow disk. You can see some kind of pinch field or area of detachment is not very perfect, but still can measure the curvature of this pinch field from these polarization segments. So now we have everything we need. We get inflow velocity from CATO, density from the continuum, scale mass from this rotation, curvature from polarization. We can solve this equation and get B field strength in a total scale envelope on a scale of a couple hundred AU. And we get this number around 1 megauss. If we calculate mass-to-flux ratio, that's roughly at 10 to 30. Just for comparison, if we apply the DCF method on this scale, so this panel shows the distribution of B field orientation of each segment, and here's the angle difference used to estimate the angular dispersion. If we apply this DCF method, assuming the turbulent velocity is comparable to sound speed, for example, then we'll get 5 megauss, 10 times larger B field strength. Actually, it's way too large, even larger gravity. So we suggest on this scale, where it's dynamical influence, the DCF method may not be straightforward to apply unless the turbulent velocity is really low. Okay, so now we have B field strength of influence envelope on a scale of 1000 AU. We can compare that with the B field strength in the dense core with about a few tens of microgauss, which is from DCF method, and the mass-to-flux ratio is about 1 to 4. Okay, we see a mass-to-flux ratio increased by a factor of few. We can compare with numerical simulation shown by this panel. So here's mass-to-flux ratio. It's a function of radius, and this line from the numerical simulation with efficient dipole diffusion, which allows the B field to decouple from the matter. And these are our measurement at 2 different scales. So you can roughly match with simulation when it evolved with like 1 times or before time. So this result, we suggest in this source, B field could really decouple from the inflow material during this star formation process, which may help it to form and grow. Okay, so I will stop here.
Any questions? So where did you measure the curvature? So I saw the some bowl shape.
Yeah.
But also, if you go away from the central point and the curvature, I don't see any systematic curvature.
Right. So there are 2 ways to measure curvature. So one is the same as Patrick study. You can measure curvature taking every 2 adjacent segments. So you can feed the radius of curvature to every 2 segments. The other thing is if we assume the field structure symmetry with respect to midplane, then we actually can calculate curvature for every segment. So it gives us a range of curvature. So that's included in this range as an error or uncertainty and propagate to a final field strength. So we do get a range of possible curvature.
For the decoupling of magnetic field of ions from neutral particle, actually, I think from Schu's paper, he already predicted that the inflow velocity of neutral particle will be different than the ion particle. I think ALMA haven't actually looked into this aspect, so maybe we can consider to explore.
So we have a paper trying to probe ion neutral drift in one foot source, and we did only get the upper limit. And we now put in a new proposal to this source as approval cycle 10. Hopefully we can get the ion neutral drift velocity for this one. And for this one, we know the field strength and we know curvature. If we really detect the ion neutral velocity drift, we can derive the magnetic diffusivity of the particle diffusion.
That's great. Looking forward to see your result.
That is very impressive. Okay, great. Let's thank Hsi-Wei Yen. And now we'll move to the last talk of this magnetic field star formation session with Maite Beltran.
Okay, hello. I put up here is a project that I started, we started back in 2009 with Josep Miquel Girart, and we started this project with the SMA, and this was after he published his paper on INAF-4A, in which he had seen the famous hourglass shape of the magnetic field in ALMA starting. So after that, we wanted to know which was the situation in the high-mass regime. We wanted to know which was the role of the magnetic field in the high-mass regime. And in particular, we wanted to know whether there were hourglass-shaped magnetic fields also in the high-mass regime. And as you can see here, the answer was yes. So after this work, what we have been doing is that we have always pursued more and more high-angular solution. So in this talk, what I will show you is how we have gone from here to the new result that we just obtained. So, oops. So just a little bit of history of Qizhou. This is a hot molecular core which is located at about 4 kiloparsecs. It has a luminosity of about 5,000 solar luminosities, and it has a mass region of about a few hundred solar masses. Here you can see that the bigger region, as seen in the dark, is dark in the infrared, and the oil is embedded here. And you can also see the result of material straight up into X-ray, which is just bringing material to assembly. The core it has several smaller cores, but the main core has a mass of about 7 solar masses, and is associated with rotation. It has a strong velocity gradient that we discovered many years ago, and this was one of the sites for particularly discovered in a high-mass regime. So the way it's associated with rotation is also associated with fragmentation. So what we thought it was a single core, single source, is in fact it has been fragmented with at least 4 embedded protostars which have masses around 15, 20, 25 gas masses. And each of them is informed. And here, informed in this case, we have seen it in CSIC. Qizhou has shown us the ammonia. So here we can see the redshifted absolute and CSIC, in which all the K components of CSIC are similar social. And each of these sources is also associated with molecular force. Oops. Okay. So as I already told you, we observed this with the SMA at 1 second resolution and 870 microns, and we detected the hourglass shape that I have already told you. So the magnetic field was pinched along the major axis of this algebraic structure. What we thought it was a rotating fluid, and in fact the magnetic field was parallel to the rotation axis of the structure. In this case, the magnetic field strength that we derived using the Chandrasekhar Fermi method was about 10 millivolts, and the mass to magnetic flux ratio was about 2.7. So this was supercritical, and this in fact was corroborated by the fact that we had detected inverses in profiles, in this case in C34. So at that time, we thought that the rotation velocity decreased with decreasing radius. We used for this methanol, and we thought that okay, this is demonstrating that the angular momentum is not constant in the nebula. So we thought that what we had seen also in this source was evidence of magnetic braiding. So later on, we continued observing this source, and in this case, we went to high angular resolution. In this case, it was 0.1 seconds with ALMA. And here, what you can see here, observation of CSIC and different transitions at different energy, excitation energy, from going from about 100K to 400K. So what we saw is that the collision velocity plots were indicating that we have rotation in the core, but we also see that the higher the excitation energy, the steeper was the slope. So what this is indicating is that, in fact, the rotation energy speeds us toward the center. So this is what you expect in case of angular momentum conservation. So this is better seen here, which we have divided the CSIC chain by rationally excited, which is higher energy transition divided by the K equals to transition, and we can see that the maximum of this region is reached throughout the center position. Okay, so marijuana use. So we went to ALMA, and we besides the molecular emission, we also observed the full polarization, the gas polarization observation. So in this case, we observed at 1 millimeter, we use ANSI, and again, we use a 0.2 nanosecond resolution. So this is 5 times better than the resolution we got with the SMA. Here you can see the stock height with the main core here and all the foreign embedded sources. And we observe a magnetic field pattern morphology similar to what we have observed with the SMA. So the direction of the magnetic field was here, again, it was in the direction of the rotation axis, and this was also the result that we obtained by modeling the magnetic field. We modeled the magnetic field with gas core, which was developed by Marco Padovani, and in this case we use a symmetric singular toroid threaded by a colloidal magnetic field, in which we added a parallel component. So we fitted the observations with the model, and we found is that G31, a 0.2 second resolution, can be well represented by a purely colloidal component. The toroid component is very small, it's a rate of 10% or even less. So despite we have a strong rotation evidence in this core, the rotation seems to have no effect on the magnetic field. Again, we use the Davis Chapter-Second method, and we obtain, in this case, by applying the information that we have obtained from the modeling, a magnetic field strength over the order of 10 milligrams, similar to what we have obtained with the SMA. And again, the mass-to-flux ratio indicated that the core was slightly supercritical. So, as I probably told you in the beginning, the main core is not just a single core, but it has fragmented, and it has a 4 sources embedded, and here we can see in color we have 1 millimeter, and in both of the white color we have the 3 millimeter data, in this case at even higher angular resolution. Here we are going to at 80 milliseconds, we are tracing 300 AU. So we wanted to know how was the magnetic field at this smaller scale. So again, we went to ALMA, we applied also for time at 1 and 3 millimeters, and we obtained this. So the magnetic field seemed to be similar to both wavelengths at 1 and 3 millimeters. So this describes that what we were observing could be dust scattering, but it was again similar to what we have observed with the SMA. So here we have the comparison between the 1 and 3 millimeters, and it was quite similar all around the core, except for a small area here. This is the area between sources B and C, and in this case, the direction of the magnetic field, the magnetic element was orthogonal between 1 and 3 millimeters. So we explain this as due to dichroic extinction. So dichroic extinction is seems to be present in this core, but only in a very, very small region. So we interpreted this as a fact that in order to dichroic extinction to work, it needs really high density. So again, we model the magnetic field. In this case, we model the 1 millimeter magnetic field using the same model we had used before. And again, we obtain the same. So the best model is a purely colloidal field model, oriented in this direction. The red line here indicates the direction of the magnetic field, and with a mass-to-flux ratio, which is consistent with being supercritical. So we use the Davis Chapter-Second method, and we obtain a range of magnetic fields between 13 and 78 milligrams, and this depends on the density we use. So we use a density which is average more or less in the whole core. It gives us 13 milligrams, but if we take the densities obtained towards the central part of the core, if we just take the densities obtained at the highest angular resolution, then we get about 78 milligrams, and mass-to-flux ratio of about 2. We also use the polarization intensity gradient method developed by Patrick, and in this case, we obtain the same. So we use the sigma parameter, that is parameter to tell us which is the relative importance of gravity of magnetic field and gravity forces, and we obtain that gravity, the magnetic field cannot prevent collapse in the core. And we also estimate which is the magnetic field in the plane of the sky, and we obtain values which were quite similar to the ones we have obtained with the Davis-Chandler method. And again, the same for the mass-to-flux ratio. So, to conclude, this is what we got. So, going from the SMA tracing scales of about 4,000 AU to ALMA tracing scales of about 250 AU, we have seen that the magnetic field keeps being the same, the direction is consistent, is always the same, and also if you take a look, the polarizing density is the same. So it seems to be like a self-similarity of the magnetic field when we go from large scales to small scales. And this is something that, I mean, we thought we should have happened. So if you take a look to the theoretical models, when we go from core scale to circumstellar scale, the magnetic field should start changing. So you should move from a polygonal configuration to a more toroidal one. So the magnetic field should start to get changed. And this is what we are observing. So at some point, we thought that we could have a problem of opacity. So despite we are having more and more and higher angular resolution, we are not really tracing what's happening on the smaller circumstellar scales. So we thought that the only way to solve this and to see whether this similarity is real or is due to opacity, we will have to go to wavelengths which are longer, so not even 3 millimeters can give us the answer. So we probably will have to go to band one with ALMA and try to see whether we can get the same or whether we trace something different and real circumstellar scale. So with this, I'm moving to the conclusion. So I have just shown you how we have evolved from the knowledge we have from the magnetic field in history from what we know from the SMA to what we know with ALMA. We have seen that the magnetic field system hasn't changed that much, going from core scales to what should be circumstellar scales. They are about 10 to 20 gigas, which are pretty high. And this suggests a similarity, but we have to be cautious. So we cannot discard that this could be due to the both 1 and 3 millimeters are optically. Thank you.
Questions for Maite? So I want to ask, taking into account the effect of rotation on the lines when you estimate the magnetic strength using BCF method.
Sorry, can you repeat?
So they're taking into account the effect of rotation on the velocity values when you estimate magnetic strength with rotation, with BCF method.
Yeah. I mean, the rotation has been taken into account to estimate the length.
Yeah, that's the question.
Yeah.
Oh,
So if you think the angle difference between 1 millimeter and 3 millimeter between this implication is due to the dichroid effect, and you think it only happens in dense region, then why you don't see that in the core itself?
Because probably here,
Yes.
this is a very dense region. So even though the emission is optically thick, the rest is not optically thick enough to produce a direct emission. So only here is where you have enough density to produce the effect.
Yes, but in A and B and C there's cores.
Yeah. Well, but here is the only way where we see this orthogonal difference between the segments. So I agree with you, you should expect having something similar here.
Yes.
The thing is that here, for example, the 3 millimeters has not been sampled, because the 1 millimeter data is better sampled. So here you see that we probably did not have enough sensitivity envelope, so we don't have 3 millimeter polarization data. So it could be that here you also have, but we only detected in this small region.
Yeah, but you also see that this particular feature down there towards the south. Yes, yes. It's not perfect, but
Yeah. Let me, okay, let me.
Yeah, I would like to answer. Now, your point is a very good one. However, at the positions of these four fragments, you can confirm that mine, right? There is a very strong contamination by line, especially by line emission, but especially by line absorption. So I would not trust what's going on just at the peak of the A, B, C, and D process. Because basically you are dominated, this is about millimeter, you are dominated by line emission and absorption.
So here comparing, let's see, this is the area I'm talking about, but also this area is where the differences are higher between the 3 millimeter and 1 millimeter. So there is also a small area here, some here, and here. But the strongest one is it keeps into this one here.
Go ahead.
That's not my fault.
So maybe related to this, but so for both wavelengths, the 1.3 and 3 millimeter, the detection is relatively patchy, so it's not connected to the magnetic field structure like the coarser resolution.
Yeah.
Do you know why that is? I mean, you mentioned maybe opacity or is there something more hidden in the areas where there is no detection?
We don't know. We expect to have something more like what you have shown, in which you have segments everywhere, but here is quite patchy, so we don't know why.
The polarization density is coming from extended envelope, so you pick it very well in the compact configuration with ALMA. So another possibility is most of the polarization we saw with SMA is in the extended envelope. So we pick it very well with the compact configuration, but we also extended a significant fraction of this polarization is just resolved out. So just see the inner part.
I'll ask a follow-up to that. So ignoring the line contamination, what's the spectral index look like between band 3 and band 6?
Okay, so we have a map. I haven't put it because in 10 minutes, 12 minutes, you don't have time of that. But it was slightly higher than 2. So I don't
So
know.
it's partly thick.
It's partly thick, yeah. Yeah.
All right, let's thank my team again. And I suppose we go to coffee break and we come back at 4. Okay. Thank you. I think
Yeah,